You tell me. Huh?
Yeah.
Hello, good afternoon, everyone. It's my great pleasure to introduce you Angela Madeo from Lyon in France. And she is going to talk about metamaterials and their way of being described by micromorphic elastic continua. So Angela, it's your
turn. Thank you very much, Mohamed. Thanks to the organizers for this nice invitation, which was much appreciated. So as it was said, I'm going to present you a kind of unusual approach for metamaterials, and namely how we can use enriched continuum models, and in particular micromorphic models, to model these materials at the scale of the engineer. Before starting, let me just acknowledge this recent ERC funding, which is related to a project that is going to start next September. And just let me spend a few words, because I'm now looking to hire new people. There is still some free available positions, mostly for the PhD level. And what I'm presenting today can be seen as a preliminary of what will be done in this project. So namely, propose new enriched models for metamaterials modeling. And the big step forward will be that of answering to the question how we can combine metamaterials with more classical materials. So how we can complement such micromorphic models with well-posed boundary conditions, so that we can, in such sense, play Lego with such metamaterials. We can combine these metamaterials to more classical materials, or also different metamaterials among them. So the idea is to open the way to engineering design of structures using in the conception phase such metamaterials. So here I sketched some ideas on what will be possible after this research is performed. And we can think, for example, to a noise and vibration controlled railway station, as in the picture. You think the pink is the metamaterial part, and the gray is more classical materials. And one question that we would like to answer is how we can shape the vault of this station, for example, to convey energy into the classical material and to convey energy towards specific collection points. So the same idea, you can think to a metamaterial which is coupled to the train rail, so as to absorb vibrations. And so how to connect this material to a network of classical materials to try getting this energy in specific patterns. And another example, we can have many, but is a city which is entirely protected from seismic waves. Among the organizers, we have specialists about the conception of shields, seismic shields for buildings. So we have today the knowledge to conceive and maybe produce such kind of elements, but there is problem in how to connect such elements, such new elements among them and with classical materials to try to convey this seismic energy in other collection points. So to arrive at this point, we have to make some words about this micromorphic continuum. This is a usual introduction that I make in conferences. And what do we mean with the word metamaterial? Here in the audience, I guess we are more or less all acquainted with this concept, which starts a little bit early, already in the 90s with lakes. We didn't talk about metamaterials, but we started seeing appearing materials like foams that exhibit negative Poisson ratio, and then research is going ahead in this direction. And here in the slide you see different materials with exotic static behavior. So in the static regime we have also specialists in among the organizers how to construct, to build unfillability clocks and so on and so forth, or different deformation patterns which are triggered by different levels of the applied load. If we take the dynamic regime, things become even more interesting if possible. And we can think to well-known band gap metamaterials, a lot of research on this side. Or as I said before, we have experts on seismic cloaking. Prototypes have been produced. And we have a lot about lensing and so on and so forth. Of course, depending on the unit cell size, arranging suitably the mass inside the unit cell, you can, and playing with the dimensions of the unit cell, you can think to filter out or to manipulate waves at different frequencies. All of this we can do today. Okay. As you know, such metamaterials have a quite complex dynamic behavior that can be recognized via dispersion curves, for example, which can be thought as a fingerprint of the metamaterial. So once we have fixed the microstructure of the metamaterial, we can perform standard, let's say, block Floquet analysis or other methods which are available, and we can obtain such dispersion curves, which tells us a lot about the metamaterial. For people which are not acquainted with the concept, you have the tangent to this curve that will give you the speed of the wave propagating into the metamaterial. And you can recognize acoustic optive curves, the acoustic ones starting from 0, which are directly related to the stiffness of the material used to produce the metamaterial itself. And the point is now how we can study metamaterials behavior. As I said, there are different approaches which come into the picture. For people who are familiar with Cauchy elasticity, Cauchy continuum mechanics, we must say that this approach is not adapted to describe such the behavior, such a complex behavior for these materials. For example, here we see in the picture the yellow part, which is the region that can be described by Cauchy elasticity. I will make a very quick recap of that, but Cauchy elasticity only allows you to describe acoustic curves without dispersion, so the linear part of the acoustic curves. Then you have the green region, which is a little bit more extended, and you can achieve this like with enriched theories, which are known as second gradient theories. I will try to give a brief sketch of all these theories are about. So with second gradient theories, you are always in the acoustic curves region, but you can start seeing some dispersion, so where the curve starts bending. And then you have all the homogenization methods that allow you to go higher in frequency, for small or even higher wave numbers, you can spot your dispersion curves to see, to model the material behavior. Our goal here was to say, can we find an enriched continuum model that is able to describe a sufficiently interesting range of frequencies, so that includes the band gap, for example, and which is simple enough, so which consists of few enough parameters to be handled and to try keeping a physical insight in the mechanics of the material itself. So the answer is just here on the right, and here I present already the results. The black lines are the fitting of our micromorphic model that I will introduce in some minutes on the block-Floquet curves that we use as an experiment in this case. Okay, so the point now is how to introduce this micromorphic continuum. Before getting in the detail, because I understand that can be a little bit too quick to start directly with micromorphic continua, I decided to give a brief recap about Cauchy elasticity so that we can get familiar with the notations and the tools that are used afterwards. So for micromorphic, I will not give details too much because calculations become too complex, but we can start following the ideas and the concepts which are behind with something we are acquainted with. So here you have a classical Cauchy continuum scheme, the classical potatoes. You have material particles capital X, which are mapped in their current position small x with the mapping key, or equivalently with the displacement. So in Cauchy mechanics, Cauchy classical mechanics, we say that the medium has 3 degrees of freedom, which are the 3 components of the displacement. Once the kinematics is fixed, we will see how to generalize this concept. We introduce strain and kinetic energy density. Here is for a classical isotropic linear elastic medium. And the kinetic energy goes as well. So here you can just see which are our notations with derivatives with respect to times and so forth. What we do with this strain and kinetic energy is to apply standard least action principle, and we get the equation of motions either in weak or strong form. So here in red, you can see the classical balance of forces for Cauchy continua. The only point is we derive such equations using the principle of virtual powers. We have in Cauchy elasticity other ways to do, but we follow a variational approach, so principle of virtual powers or least action principle, because it's the only way we have to generalize our concepts to micromorphic. So postulating the principle of virtual powers, we get our strong form boundary conditions if we integrate by parts, so on and so forth. But more interestingly, we also obtain the boundary conditions which are intrinsically consistent with our system of PDEs. So for Cauchy continua, we all know the results. If we perform our variation, we end up with duality condition, which tells us that given a Cauchy body, a Cauchy continuum, we can act on it from the exterior, either assigning a force, which is equilibrated by the Cauchy stress, or applying a displacement on the boundary. This comes directly from variational principle. And if we also take an interface between two Cauchy continua, similarly, we will impose on this discontinuity, we will impose the continuity of traction and the continuity of displacement. So here we are all happy and familiar. To continue the treatment that we make with such equations, now we take the equations of motion and we want to study plane wave propagation. So just to sketch the results, already for Cauchy, I take the simple 1D case because calculations are very simple to do also by hand. And so what we say is, okay, we start with our equations of motion. We consider a case in which our unknown field, which is the displacement, only depend on one space variable x instead of the wall position vector. So with this only hypothesis, our vector equation of motion here simplifies into three scalar equations which are uncoupled. So for 1D is a known result. For Cauchy continua, we have three uncoupled equations, one for longitudinal displacements U1 and two for the transverse waves. What is done classically is to say we take plane wave ansatz for the displacement. So we say each of these components of the displacement takes this exponential form with the frequency omega and the wave number k, and alpha are the amplitudes, the wave's amplitudes. The manipulation is very simple. We take these ansatz, we plug into our PDEs, and we get the well-known dispersion relations for Cauchy media. So basically the relation between omega and k. So the result for Cauchy we know, and it's, if we look at the dispersion curves in the frequency wave number plane, we just have two straight lines for in plane. Okay, so one slope is the blue for longitudinal waves, and the slope of the green one is for in-plane shear. And with the third equation, we get a straight line for out-of-plane shear. So as I said in the beginning of the presentation, this model is too simple even to describe dispersion. To close up our problem, we take now an interface because we want also to work with boundary conditions. We take the 1D case. So in this case, we have one incident wave, one transmitted, one reflected. Given, assumed that the incident wave is known, so here we have everything known, we have two unknowns in the problem, which are the two amplitudes, okay? Because everything else is known, we say the frequency of the incident wave is known, it is the same for all other waves, and the k is known from dispersion curves. So we have just the two amplitudes unknowns, and these amplitudes are classically determined by imposing boundary conditions, or in this case, continuity conditions at the interface. The solution is unique because the problem of elasticity, we all know it is well posed. A classical way to visualize such repartition of energies between transmitted and reflected is obtained from conservation of energy, where we take the total energy E as the sum of kinetic and potential energy, and we write its conservation in this form, where H is called the energy flux, is related to the Poynting vector, and so on and so forth. But the interesting thing to say is the expression for H in Cauchy elasticity is well known, is just the Cauchy stress times the velocity. And with the micromorphic medium, we will see it takes a more complex form, but the idea remains the same. The conservation law will take exactly the same form with a little bit of terms more. The advantage of this energetic approach is that we can introduce reflection and transmission coefficients starting from this energy flux. And now we get a little bit more in the details by introducing such micromorphic framework. So we see our continuum mechanics scheme that I reproposed before. So we have the classical two potatoes with your material particle capital X, which is mapped in its current configuration. So we have the displacement map key, or equivalently the displacement, 3 degrees of freedom. But now we do something more, and we extend the kinematics of the continuum by saying that at each material particle, capital X, is associated a kind of microstructure in a general sense by introducing a new map, which is this tensor P, which depends, of course, on the material particle position. And this tensor P is called the microdistortion tensor. And in general, it is not symmetric. So we are adding to the 3 degrees of freedom of displacements 9 extra degrees of freedom, which are the components of this matrix. And this matrix is just deforming the microstructure of the medium, which is embedded in capital X. Once we have the kinematics we have seen with Cauchy, the Cauchy example, we just need now to give constitutive laws for the energy, kinetic and potential energies. And in the literature, you can find a certain zoology of different enriched continuum models. And basically, the difference among them is the hypothesis done on the energy. So when we talk about micromorphic media, we are taking these 3 plus 9 degrees of freedom, displacement and microdistortion. And we are saying that our constitutive law on the energy depends on the gradient of U, as in classical elasticity, its symmetric part indeed, on P, and also on its gradient. This is the general micromorphic model. If we restrict again the kinematics to U alone, so only 3 degrees of freedom, but in the strain energy, we consider more than the first gradient, also the second gradient of U, we are talking about second gradient models. So given this restricted kinematics I showed in the beginning, we are not able to treat metamaterials with that. Then we have this relaxed micromorphic that we introduced in our team recently, which keep the whole kinematics of a micromorphic medium, so the whole 12 degrees of freedom, but in the energy, we are not taking the whole gradient as is done in Midlin-Ehringen models. We just take the curl of P. So it's rotational part. Starting from this relaxed micromorphic model, if we take the symmetric part of P to be vanishing, we end up in a so-called Coursera model, which is also well known in the literature. So basically, you say the symmetric part of P is 0, only the skew part of P remains alive, which has 3 degrees of freedom, plus 3 Coursera continuum also only has 6 degrees of freedom, and with a specific constitutive law. We could go longer and longer in the literature. You can find a lot of different models, internal variables, when you don't have any derivative of P in the energy, but just P, or coupled stress, where you take some just Cauchy kinematics with U, 3 degrees of freedom, and then you put some gradients, the gradient of the car, etc., etc. So the point is, now we have a lot of generalized model, which one to choose to describe the phenomenon in which we are interested. What we did is to start with this micromorphic model, relaxed micromorphic model. For those who have already heard about Midlin-Ehringen elasticity, which is the difference? The difference is that here you can see in the explicit expression for the strain energy, the potential energy, we can see this Sims-Q decomposition of the deformation measures, which means we are introducing these tensors. And if we sum the components of these tensors with respect to a full micromorphic model, we end up with a lot less parameters than in the classical case. So just to keep in mind, we have a nice Sims-Q decomposition of our deformation measures, which has the symmetric and the skew-symmetric part of P, grossly speaking, and the classical part with the sim gradient of U, but we also put a skew-symmetric part of gradient of U. And then we have the curvature term here, which introduces a characteristic length. Given that we want to study the dynamics of metamaterials, we also need a generalized kinetic energy. So here you see the standard part with the north square of the velocity. And we also have terms which are also apparent in Midlin-Ehringen models with the derivative of P in some sense. Here we keep this decomposition in Sims-Q part, but there is no difference with Midlin model. And then we also introduce a new term, which is usually not considered in this micromorphic framework, which is the time derivative of the space gradient of U. So in the beginning, if it was not even clear for us that this should be considered, but at a point we got aware of the fact that if we don't consider this term, you look at dispersion curve, at your dispersion curves, and they all have oblique asymptotes, which means it's a little bit far from the experiment that we want to fit. So if we remember a bit, we will look at them again later at the Bloch-Floquet dispersion curves of typical metamaterial. You always have curves that are getting quite flat. And what we ended up is that with a coupled space-time derivative of this time, the kinetic energy, you can effectively have this flattening effect. Okay, so now I don't repeat the conceptual framework, which is the same that we did for Cauchy elasticity, but the point is we have an energy, we have strain and the kinetic energy. We can build our action functional, the power of internal action, postulate that it's the same of the power as the power of external actions. The only thing is that for micromorphic continua, this is the red one. Okay, the external actions are a little bit generalized with respect to Cauchy settings, because we can act on our body not only with forces, so here in the bulk and on the boundary, but we can act also with the dual quantity to the tensor P, which means we introduce internal action, which is called the double force, either in the bulk and both in the bulk and on the boundary. But once this power of external action introduced, we can make exactly the same as we did. We postulate the principle of virtual powers, or at least action principle. And we can end up with the equations of motion for our system. Here we arrive to the strong form because we want to study wave propagation. So what we get is an equation which is the balance of generalized force, which is dual to the displacement, okay? And this generalizes Cauchy elasticity in the sense that you see here, you have this divergence of sigma tilde, where sigma tilde now does not contain only sim grad u, but also contain the sim skew part of P and the skew part of gradient of U. So it's a generalized stress. And related to that term in the kinetic energy I showed that had the flattening effect, we have a new term here with this sigma hat, which contains second time derivatives of the gradient of U. Okay, so this generalizes our balance of forces, but then we have another tensor equation, which is the balance of double force, which is dual to the micro distortion. And here, for convenience, we separated this tensor equation in two equations just involving the sim and skew part. We can put all together, but this is more nice to show. So basically, we have one vector generalized equation plus 9 scalar extra equations. The point is, our variational approach allows us now to say how we can act on a body, on a micromorphic body from the exterior. So if we take our continuum and now we think it to be micromorphic, we can act as it was before with forces on the boundary, okay, which are balanced now by this quantity, which is the generalized traction, okay? So we have this generalized Cauchy stress applied to the normal. Or we can act with imposing displacement. This doesn't change, but we have extra possibilities to act on our body, namely with this double force phi or its dual part. In the relaxed framework, we just have to assign the tangent part, but this is not important now. The important point is we have well-posed boundary conditions, which are intrinsically compatible with the PDEs. We have unique solutions for other ways. Then we proceed exactly as before. Don't want to bother too much. The only thing is that we have our unknown fields we have understood now are the displacements and these components of P, our 12 degrees of freedom. So all the unknowns, we make a plane wave ansatz for the displacement and for the micro distortion. We replace in our equations of motion, which were here, and we just calculate a bit simple algebra, and we get to a PD system that reduces to an algebraic system of the form a matrix time a vector V, where V is the vector of the unknowns, or the 12, equal to 0. So our PDEs are replaced by this algebraic system, which has non-trivial solution only if the determinant of D is equal to 0. So from this condition on the determinant, we find all the roots omega as function of K, which are our dispersion curves in this framework. Okay, so here I present in black the results, but of course we will need to talk a little bit more on how to how this fitting is obtained, because it's no magic that it already fits our metamaterial. We need, once we have the general expression for the dispersion curves, we need to establish a procedure to fit our elastic parameters on a true metamaterial. Okay, so as you can see here, I presented both the dispersion curves at 0 and 45-degree propagation to show that with this relaxed micromorphic model, we are able to catch also the anisotropy of the material. You see that here you have a stiffness, here you have another stiffness. This is due to the fact that the material is not isotropic. And this is nicely reproduced. Okay, so we need to fit on a realistic, on a true metamaterial. We used for the beginning this cross-shaped. Then we are going ahead with other microstructures. And so here is the unit cell. And here is some specimen of containing more unit cells. To validate our model, what we need to do, we need to first calibrate, as I showed, on our micromorphic model on the metamaterial. Then we have to validate this calibrated model on a bulk propagation problem. So compare our micromorphic results on an infinite structure to the detailed microstructured case. And then we need, again, an independent experiment on the reflection and transmission and see, does our model fits also the reflection transmission problem. Okay. So we have a little bit of time, so I will try to sketch the basic features of the calibration procedure. So we have our model, as I showed you in the energies, we have all these tensors which contain parameters inside, how we can calibrate such parameters. What we did is to separate the static and the dynamic problem. So we start from determining the static parameters. For this, we start simplifying our equations of motion. We say, okay, we neglect the micro-inertia terms, so the time derivatives on P, and we set the characteristic length to 0. So we are considering large specimens. With this hypothesis, the second governing equation that I showed you before reduces to a particular form. So we can manipulate, replacing the first equation, and our system actually reduces to a unique equation, which is this one, and which is a Cauchy type equation, in the sense we have the divergence of some elasticity tensor sim grad u equal the rho acceleration. Okay, so it's Cauchy type. What we can say is thus that this tensor, which contains the tensors of our micromorphic model, all this combination of our tensors, is equivalent to a macroscopic elastic tensor. So we set C macro is equal to this combination. The advantage is that now the C macro we can compute. We have a way to compute it with standard mechanical tests. So I will say in a while, but this is known by standard mechanical tests. We introduced some way to estimate the C micro, I will tell later. It means that via this formula, the CE is automatically determined. So let's see how we can estimate C macro. C macro is the standard elasticity tensor. So either we calculate it by estimating the slopes of the Cauchy curves. In the isotropic case, it will be related to lambda, mu, or the Young modulus and Poisson ratio, no matter. Okay, it's just we take our tangent to the Bloch-Floquet acoustic curves close to the origin. We compute the value of the slope of these curves, and we can directly relate to the C macro. Or, to be more precise, we can use what we did in some of our papers. We can use classical periodic homogenization to get the C macro, which is correspondent to the homogenized version of our metamaterial. So the point is, C macro can be calculated easily. A little bit more difficult is to estimate the C micro, which we know to be related to the microstructure. And so we tried, in some sense, to relate its measure to something to be measured on the unit cell. So as you know, in a periodic metamaterial, we can have infinite ways of choosing a unit cell, because we have the one I presented, but the same metamaterial can be reproduced by a repetition of this other mass with springs, for example, or these other cells, or infinite others. So what we did is to say, okay, we cannot make a procedure on an infinite number of cells. What we did, we restricted only to those cells who kept the same symmetry of the metamaterial. So this material is tetragonal, has tetragonal symmetry. So we just restricted our attention to cells, unit cells that keep to be tetragonal, which were only 4. And at that point, we enforced this inequality. So we said, okay, we want in some measure find the C micro, which is greater or equal to this CKUBC, which is the strain, the stiffness tensor, the elasticity tensor associated to each of these cells when imposing kinematically uniform boundary conditions. So this is imposing kinematically uniform boundary condition is standard, is done in numerical homogenization. So we impose displacements on the unit cells. We compute by numerical homogenization the stiffnesses of these cells, and then we say our C micro must be greater or equal to this in this measure, in this scalar product, where E is a symmetric tensor. Okay, so it's deformation. Okay, in this way, this procedure gives us a first value of C micro with the equality, okay, that can be stiffer, but we can adjust this eventually on the dispersion curves if needed. Okay, so this was for the static determination. Maybe I will go a little bit quicker. We have determined C micro and CE. We still have to compute a lot of other tensors that were in the energies. And if we take the tetragonal symmetry, we can count how many are left of these parameters. They are 9. So we have 9 parameters which are still free. How we fit them? Well, 4 of them can be fixed by imposing the values of the cutoff frequencies. So we know the values of the cutoffs from Bloch-Floquet. We impose those values in our model. So we kill 4 parameters, and only 5 parameters are remaining free. And this we adjust gradually, starting from 0 to fit our block-Floquet experiment. Okay, so that was for the fitting procedure, and now I will just quickly go in the results some few minutes. We said once the model is fitted, we validate it on a bulk propagation problem. So we take a 2D plate. Here is the wall microstructure. Here we did the same with the micromorphic continuum. And we apply a pulse in the center. So we take a concentrated pulse just because we don't want to reach the boundary too early, but this is not the interesting point. The interesting point is if we now look what's happening at low frequencies after the application of the pulse. Here we have the evolution for the microstructured, the micromorphic, and the classical Cauchy. Okay, so for low frequencies, there is no surprise. All three models give the same results. At low frequencies, we saw that Cauchy close to the origin is still good. But when we get higher in frequencies, namely here is for the bandgap frequency, we see microstructured and micromorphic give you the localization. So the signal is not transmitted, is not don't travel in the medium. While for Cauchy, you can see you always have propagation because you have straight lines at any frequency, you will have propagation. So no way to use Cauchy for metamaterials. And at higher frequencies than the bandgap, namely where we had a flat curve, a local resonance, still we have even more evidently Cauchy doesn't work. Okay, the same for shear waves. This we can go very quickly. We put an interface because here, to conclude, our final goal is to go towards finite size structures. So we want to put boundary conditions in the affair and to see, can we model something realistic? And okay, this we saw for Cauchy continua. The only interesting thing is the flux for the micromorphic, of course, will involve your new quantities, but you can define reflection transmission as usual. And we treated this problem of a slab, so finite size slab in this direction. So it's a finite thickness. We have a plane wave impacting on this side. We know exactly in the micromorphic framework which conditions to impose if this metamaterial is embedded between one Cauchy continuum here and another Cauchy continuum on the other side. So, and namely the conditions were said before. We have continuity of displacement, of generalized traction, of microstrain, and of double forces on both the interfaces. In this way, we calculated reflection and transmission coefficients, and you can see here for longitudinal incident waves, we have here on the y-axis, we have the frequency of the incident wave. On the x-axis, we have the angle of incidence. We said we are anisotropic, so we are spanning all angles. And the color of these pictures give you how much energy is reflected or transmitted. So where it is blue, everything is transmitted. For example, here we are in the bandgap, the wave reaches the metamaterial, everything is going to be reflected. So no transmission, zero transmission. And we see the comparison between the whole microstructured simulation and the micromorphic. And we see that for all angles of incidence and for all frequencies up to containing the bandgap, we have a very good agreement. And even a little bit more interesting is for shear incident waves. We catch the overall behavior for all frequencies, all angle of incidence, and we also are able to catch such kind of critical angle which discriminates between total reflection from total transmission that was observed both in the microstructured and micromorphic simulation. Okay, so what we are doing now, we still didn't publish the results, but I show quickly the thing. If we now take a true finite size metamaterial, so not infinite, what happens if we send a plane wave with an angle from the top left? Okay, here you have microstructured, micromorphic, and Cauchy. You cannot see the sample is somewhere here, but at very low frequencies, no perturbation of the incident wave. If we go higher, so here we are medium frequency before the band gap, we see the microstructured and the micromorphic. Cauchy is yet good, but it begins to deviate a little bit. And of course, in the band gap, Cauchy cannot give you the correct answer because you always have propagation. So here you will also always have something which is passing inside the material, while in the micromorphic, you are correctly reproducing this band gap behavior. And here you have other values in the band gap, higher in the band gap, and it's always the same. Okay, so I guess I'm done with time. To conclude, we introduced this micromorphic framework to study metamaterials. We showed how to calibrate on a real microstructure, and we validated our model on a particular propagation and reflection transmission problems. So now we need to start using these results to play Lego with metamaterials, see what we can do to go towards structures design. So thank you very much.
Thank you, Angela, for this very nice talk.
Thank you.
And now we have time for questions. So if you have any question, you can just raise your hand. You can also come up directly, or if you don't have a microphone, you can just write the question in the chat. So Martin.